You may have noticed that our rotational system has spherical or at least cylindrical symmetry. And so it's going to be easier if we do everything in spherical coordinates. So let me just remind you about the spherical coordinate system. So if we think about our Cartesian coordinate system that we're used to thinking about, x, y, and z, we can represent a vector r by an x, y, z position. And also, we could imagine just telling you what the length of that vector was, and then telling you about the angle that its shadow makes with the x-axis. We'll call that angle phi, and the angle that it makes with the z-axis, we'll call that angle theta. So I could give you the coordinates of this point either as r, theta, and phi, or as x, y, and z, and I could represent the same point with either one of those three coordinates. So r squared is equal to x squared plus y squared plus z squared, and x is equal to r times sine theta cosine phi, and y is equal to r sine theta sine phi, and z is equal to r times cosine of theta. So that's how I get from one coordinate system to the other. So what I need to do is I need to change my Lx operator, my Ly operator, and my Lz operator, as well as my L squared operator, into spherical coordinates, into the r, theta, phi coordinate system. So we're not going to go through all of the math, and I'm going to give you the result. So the Lx operator in spherical coordinates is I h hat sine of phi times the partial with respect to theta plus cotangent of theta times cosine of phi times the partial with respect to phi. The Ly operator is I h bar cosine of phi, take the derivative with respect to theta, minus cotangent of theta times sine of phi, take the derivative with respect to phi. And the Lz operator is equal to minus I h bar, take the derivative with respect to phi. And now you can see why we pick to know Lz and leave these unknown, uncertain. Because clearly this operator is way easier to handle than the other two. Okay, so the L squared operator turns out to be minus h bar squared, second derivative with respect to theta, plus cotangent of theta times the derivative with respect to theta, plus 1 over sine squared theta, second derivative with respect to phi. So remember that cotangent of an angle is equal to the cosine divided by the sine of that angle. There's one more thing that we need to know about spherical coordinate systems. Because we're typically going to want to integrate these functions, we need to know what dx, dy, dz is in spherical coordinate systems. So this is a small volume element, and if we're going to integrate over all x, y, and z, we need to be able to also integrate over all r, theta, and phi. And so in spherical coordinate system, this works out to be r squared sine theta dr d theta d phi. And so when we're integrating over all space, this is the volume element that we need to integrate over.